welcome Joachim Kock, who will talk about decomposition spaces, right fibrations, and edgewise subdivision.
Thanks a lot. It's always a pleasure to be in Italy, although I prefer the real Italy. And it's also great to be in the Ithaca. I think it's a very nice initiative to have this series of parties. So this is joint work, almost finished with Philip Hackney. It will be on the archive, 2 papers very soon. But a lot of what I will tell is just older stuff about decomposition spaces, and that's joined with Emma Galvis and Andy Tonks. So I will start with some introduction about decomposition spaces, just enough to understand the theorem I want to present. Then I will write down the theorem, and then I will explain as much as I have time to about the ideas and the proof of the theorem. I don't know how much I come to the proof, but at least the motivation and hopefully also an application of the theorem. So to get started with decomposition spaces, maybe we should start in combinatorics. So in combinatorics, coalgebras, bialgebras, and Hopf algebras express decompositions. So it's used a lot in algebraic and enumerative combinatorics to break down structures into smaller structures until you get down to the atomic structures, and then you can get recursions and you can count what you are interested in or understand structures. So here's an example. It's called the chromatic Hopf algebra because of its use in the graph coloring problems. Hopf algebra. So as a vector space, it's spanned by the simple graphs or the isoclasses of simple graphs. And then I will tell you, this is simple graph, what is the co-multiplication of this coalgebra. So I should take a graph and tell you how to co-multiply it. And you do that by summing over all ways of splitting the vertex set. So V is the vertex set of the graph into 2 disjoint subsets. And then you take the graph and you restrict it to one of the subsets of the vertices and put it on the left, and you put the restriction to the other vertices on the right. So you need vector spaces in order to be able to take this sum, but other than that you can see that it's a completely combinatorial description. So just as an example, inside this sum, if the graph looks like this, for example, let's see, then among the many summands, there will be one where we cut like this. So that means that the left-hand side of the co-multiplication will be this, and the right-hand side will be this. So this is a typical example of combinatorial Hopf algebras. I didn't say what the algebra structure is. That's just disjoint union of graphs. And I didn't say what the antipode is. That's a little bit more complicated, and it's always an alternating sum, and but it's pretty formal. Now, often decompositions arise from compositions. And the best theory for composition evidently is category theory. So if you have a small category, it should even be locally finite. Then we get a coalgebra structure on the free vector space on the set of arrows. So C1 is a set of arrows, and it's defined like this. You take an arrow and you co-multiply it by summing over all factorizations of the arrow. So you write f here, and you factor it into A, B in all possible ways. And then you simply put the arrow A on the left and the arrow B on the right. And locally finite means precisely that this sum is finite, so it makes sense in the category of vector spaces. So this is Leroux. '75. And he found this as a nice generalization of two things that had been used extensively in combinatorics, namely Rota's theory of incidence coalgebras of cosets and Cartier-Froitat for monoids. And in both cases, it's just the observation that we now take for granted that posets and monoids are special cases of categories. So if you take this formula and specialize to these two special cases, then you get, you subsume a lot of theory from the 60s. So this is the 60s, and this is also the 60s, but maybe a little later, 69 maybe, I don't know. So in this way, we see that decompositions arise from compositions. Now let's take a simplicial viewpoint because we are ending up in simplicial homotopy theory. So let's write down the nerve of a category. And now we write the whole formula in a simplicial way. So we're now talking about the vector space generated by the one simplices. And let's call a one simplex F, thinking still as if it were an arrow. And now I just write exactly the same formula, but I write it simplically. So it means I should take all two simplices such that the long edge is equal to F. That's clearly what we see in the picture. And then I should extract the two short edges. So that's D2 and D0. So now I have written the formula for any simplicial sets. I could actually now forget that I was thinking of a category. It's just a simplicial set. And in fact, I could also let it be a simplicial groupoid. That's very useful in combinatorics. Oops. Or it might as well be an infinity groupoid. So a simplicial object in the infinity category of infinity groupoids. Now, this always makes sense. You can write down this. You can furthermore observe that actually you could write this on, instead of vector spaces, you could use slice categories. So if curly S is the infinity category of infinity groupoids, then I can write down this slice, and I can define a linear functor to this slice. This is the tensor product of this category with itself. And then I ask for a linear functor. And the linear functor means that it's given by a span. Well, it also means that it preserves colimits. So the span that gives this formula is this one, where this is D1. So we pull back along D1. That means summing over the fiber over our one simplex F. And then we just return the two factors with the other phase maps, D2 and D0. So all this is very abstract, and it makes sense at the level of slice categories instead of vector spaces. And if you do this, then you don't need finiteness conditions anymore, because nobody is afraid of something infinite in a category, whereas we're a little bit afraid of infinite numbers or scalars for vector spaces. Okay, but not always co-associative. And the idea of decomposition spaces is just to impose conditions to ensure that it actually becomes co-associative. So
Sorry, so for tensor product, is this the same as the tensor product of presentable infinity categories then?
That's correct, yes.
Okay, awesome, thank you.
So a decomposition space is what makes this co-associative. And you can take co-associative on the nose if you go all the way down to vector spaces by taking homotopy cardinality of these things. But otherwise, it's a homotopy co-associative co-multiplication. And that means up to coherent higher homotopies. So it's an infinity co-algebra in the category of slices. So that's the idea. But how to make this formal? And that's a little bit technical. And I will write down the definition now. So first we have to observe that the simplicial category upon which everything is based, it has a factorization system, which is the active inert factorization system. The active maps, if I write ordinal like this, and here's another ordinal, then it means endpoint preserving. And what happens in here doesn't matter, it should only preserve endpoints. And the inert maps are the distance preserving. So that means that if we go from this interval to a bigger interval, it must just be like a convex inclusion here. So these are the inert. So the active maps are spanned by the inner phase maps, and the degeneracy maps. And the inert maps are spanned by the outer phase maps that I write like this, d top and d bottom. So this is an important factorization system in delta. Maybe it was first studied by Tom Leinster and Clemens Berger, but it was formalized and systematized by Mark Webber, who called it generic and free. It fits into a very big theory, but here we are only concerned with delta. So fact that active inert maps admit pushouts against each other. And the result is again active and inert. So let me use some notation. So the active maps we often write with a bar in the end, and the inert maps often like monos. But of course it does not, well, they are monos, but here it means inert. So if I write down active inert pushout like this, if I start with these two, then it exists. And let me put some letters, n prime, n, k prime, k. If this is a pushout, then the decomposition space condition says formally X is a decomposition space if it takes all these pushout squares to pullbacks. So that means here we get the k prime simplices, the k simplices, the n prime simplices, and the n simplices. And this should be a pullback. This is the condition you need in order to get co-associative. And how do you prove it or find it? Well, you take these spans and you write down everything, and you see that at some point you need this. Well, if you do it, you will only see the first cases. The first cases are x1, x2, x2, x3. This is an active map. It could be D1, for example. And these are inert. That means outer phase maps. So this could be D top. That would be D2. And this is D3. So this is one of the conditions you find if you just spell out what it means. But in order to get the homotopy coherent co-associative, you need all higher degrees. So you actually need all of these squares. Okay, so this is the notion of decomposition space. This is, I introduced this with Galvez and Tonks. And it's the same thing as the two Siegel spaces of Dyckerhoff and Kapranov. The definitions look quite different, but Mathieu Anel noticed that it's the same because some of the theorems in this are the same. And later on it took some work to actually figure out that they are precisely the same thing. But that's a longer story. It is the same thing. Okay, so decomposition spaces serve as an objective model for coalgebras and bialgebras and Hopf algebras. And in fact, we claim, or there seems to be a principle that all combinatorial coalgebras arise in this way. Of course, that's not true, because you could write down some crazy things with fractional or irrational numbers and it would maybe not be possible, but then you could also question if it's still a combinatorial Hopf algebra. Okay, now the question is, what maps should we look at? Let me just look at the time. Yeah. So what should be the maps? And the map should be the Kulf maps. So these are simplicial maps. Kulf stands for conservative and unique lifting of factorizations. So if you take your simplicial set to be a category, then these have the meanings you are expecting from category theory. So conservative means that if something becomes an identity arrow down here, then it was already an identity arrow. And unique lifting of factorizations means that if you have an arrow here and a factorization of its image, then there's a unique lifting of that factorization. And you can sort of easily see why this is important, because you want the resulting map of underlying vector spaces to be co-multiplicative, and that means in particular that it should preserve or reflect factorizations. So these induce coalgebra homomorphisms. Now, again, let's write out in simplicial terms what it means. So all this could be just a parenthesis. The definition is that it means Cartesian on active maps. So example, let's take one of the basic active maps, that's D1. So here I take D1, it returns the long edge of a triangle. And if we have here some components of our simplicial map and ask what it means for this to be a pullback, that's what it means to be Cartesian on active maps. Then we see it means that to reconstruct a triangle, we need the long edge and a factorization of its image. So it's precisely this condition. So this first example of Kulf corresponds precisely to be unique lifting of factorizations in the category case. Again, when we go to infinity groupoids, it's important to include not just this active map, but all the active maps, all of these. Okay, so now we have a category of decomposition spaces and Kulf maps. So now I can state the theorem I want to, well, which is the focus point. The theorem says that if you take this infinity category of decomposition spaces and Kulf maps, and you slice it over a decomposition space, then this is an infinity topos. So here I need to put some technical conditions that D should be resc complete. So you need to say what resc complete means for decomposition spaces, but there is such a definition, and if you restrict to infinity categories, it's the usual resc completeness. And in fact, much more precisely, we can say what this infinity topos is. It's the presheaf topos on the edgewise subdivision of D. So now I should tell you what the edgewise subdivision is. So for categories, okay, so here, that's the theorem. Now I feel safe, now I have said something. Now I will just explain as much as possible. So for categories, yes?
Can I ask a quick question? Do you have a one-dimensional analog of this theorem? Something like this is a one topos?
Yes. So I should put that here for decomposition, for discrete decomposition spaces, meaning simplicial sets instead of simplicial spaces. This is the same. And in that case, it's actually due to myself and David Spivak. So in that case, this is a simplicial set that satisfies these exactness condition. You slice over a simplicial set that is a decomposition space, and you find the ordinary one presheaf topos of the edgewise subdivision of that simplicial set. And for categories, the edgewise subdivision is more familiar. It's the twisted arrow category. So that's the category of elements of the Hom functor. And I guess the op should be here. So this means that the objects are the arrows, and a morphism from one arrow to another arrow is a 3-simplex like this. So this one goes backwards and this one goes forward. So that's why there was an up on the first one. So this is a map from F prime to F. It's such a diagram. That's the twisted arrow category. Now, again, this is something you can write much more generally. It's not particular to categories. You can do that for any simplicial object, and then it's called edgewise subdivision. And if I write down what it is, it's you put all the odd simplices like this, and then you need to describe all the phase maps. And here the phase maps are composed, the upper phase map is composed by, this one is composed by D top and D bottom, and this one is composed by 2 inner phase map. So that means that the new bottom phase maps are the old active maps, and the new upper phase maps are outer phase maps. I erased the active inert factorization system, but the upshot is that all the bottom part here is formed by old active stuff, and all the upper part is formed by old inert stuff. If you want to do it more formally, you should take the total deck. So the total deck of a simplicial object, you write down the simplicial object in 2 directions, and then you get, well, you write down a huge bisimplicial set. Sorry, I got the indices wrong. 2, 3, 2. And this is the lower deck, and this is the upper deck. Or possibly it's the other way around. And then you find the edgewise subdivision as the diagonal of the total deck. So you can also say the edgewise subdivision of X is the diagonal of the total decalage of X. Then everything is set so that it's true, but then you have to unpack it and you figure out what all the phase maps are. But there's one lemma that is important here. And it is that if X is a decomposition space, then the barycentric, the edgewise subdivision is Siegel. And if I put rest complete, then the result is rest complete. And furthermore, if y to x is Kulf, then the subdivided map from the subdivision of y to the subdivision of x is a right fibration. I put right fibration in the title, but I regret it a little bit because I don't have time to go much into right fibrations. But a simplicial map is a right fibration if it's Cartesian on the bottom phase maps. And Cartesian on the bottom phase maps, well, let's first take Siegel. If this is a decomposition space, then active inert squares are pullbacks. To be a Siegel, that means that the upper, lower squares are pullbacks. Let me just write the Siegel condition here in the smallest. The Siegel condition says that if you take top phase maps here and bottom phase maps here, then it's a pullback. And since when you take the edgewise subdivision, you get something active here and something inert here, the decomposition space condition will translate into the Siegel condition. Okay, so once we know, let me write a much more general theorem that has this one as a corollary. So this is a very abstract theorem. It's only about simplicial spaces. So a simplicial object in the infinity category of infinity groupoids. Then I don't talk about decomposition spaces anymore. Now I only talk about Kulf maps. So the category of Kulf maps into X is equivalent to the category of right fibrations over the subdivision of X. So this is completely general. It's only about simplicial spaces. There are no decomposition space axioms or anything, but we still have the Kulf condition and the right fibration condition. And what this map is, it is just SD. So it takes a Kulf map and sends it to SD, SDX, and this is now a right fibration by the lemma I wrote here. So it's clear that there is such a functor. The surprise is that you can actually invert it. I wonder how much time I have to explain that. I think I would rather go a little bit in direction of applications and why this could be interesting.
You still have 15 minutes.
Yes, that's good. So that will give me time for the applications. And if I have time in the end, I'll say something about the proof. So I should just say how to get this theorem from this one. Well, I forgot to say something important, namely that if something is Kulf over a decomposition space, then it is again a decomposition space. And if something is a right fibration over a Siegel space, then it is again a Siegel space. So if I take my X to actually be a decomposition space, then this infinity category of Kulf maps into it is actually just a slice in the category of decomposition spaces, where we only took the Kulf maps anyway. So if I instantiate this theorem with X decomposition space D, then I get this slice. And then right fibration over a Siegel space, that's by the Grothendieck construction duality, that's the same thing as a presheaf on it. And then we end up with an infinity topos. But all the proof does not use decomposition spaces at all. Okay, so let me start apparently from scratch on something else, where we will come to an application of the theorem. So write J for the inclusion of the inert maps into all maps of delta. So this inclusion plays quite a big role in the general theory developed by Mark Webber, where you actually realize that delta is a Kleisli category over this one for the free category monad and things like that. So let me just write down something. So if we have a simplicial object, no, let's just take a simplicial set. Then this is the nerve of a category if and only if its restriction to the inert maps is a sheaf. So I'd write J upper star for the restriction, and this is a sheaf. And it's a sheaf with respect to the canonical Grothendieck topology on delta inert, where something is a cover if it's surjective on both edges and arrows. So this is a fancy way of writing the usual Siegel condition, where we say that, well, the usual nerve theorem for categories. It can be written in this way. Now we are interested instead in the left Kahn extension along this map. So that means we start with a presheaf on delta inert. We left Kahn extension to get it a simplicial set, and then we ask, what do we get? So this is rarely a category. If it were, then people would have studied it a lot, but that's not the case. But it's always a decomposition space. And furthermore, for any map of delta inert up diagrams, so presheafs on here, any such map, then when you hit it with left Kahn extension, it becomes Kulf. So maybe this looks nice, but I mean, it's not super surprising, because here we have the inert part, and we throw in the active part freely by this process. And since it's thrown in freely, and since both the decomposition space axiom and the Kulf axiom is about the active maps and their relationship with the inert maps, it's not, I mean, it's not surprising that you land in decomposition spaces and Kulf maps. So now there's a theorem. I can maybe write it here.
Now that you made this so plausible, is it also true for the right Kahn extension?
I have no idea. Actually, I'm not very familiar with the right Kahn extension here.
Okay, thanks.
And I mean, it has this one. Yeah, no, I don't know. I just say I don't know. So theorem, and this is also with Philip, that this left Kahn extension induces an equivalence of infinity categories between presheafs on delta inert and decomposition spaces over the classifying space of the natural numbers. So, well, that's the theorem. So now I want to deduce this one from this one. So proof. Well, for the proof, we need two small lemmas, which are nice and not difficult. The first one is that the edgewise subdivision of the classifying space of the natural numbers is delta inert. This is easy, you just sit down and check it. And these are just one categories. There's no mystery here. And if you just want to check, I mean, if you pick out the odd simplices of this one, so that's 1 tuples, 3 tuples, 5 tuples, and 7 tuples, and so on of natural numbers, then you write down an element in delta inert, which is basically, I mean, I wrote inert maps like this, and the three pieces are this piece, and this piece. Those are the three simplex that gives a morphism in here. So that's the first lemma, and the second lemma is also quite easy, but nice to look at. It says that left Kahn extension of the terminal is the classifying space of the natural numbers. For this, maybe it would be fair if I write down a formula, at least at the object level, for left Kahn extension. So left Kahn extension of A, if I write just the case simplices of that simplicial set, it's obtained by summing over all active maps. So these are the active maps in delta, and then I just take AN. This is a formula for the objects of the left Kahn extension. And with this formula, you can also easily verify this one. Okay, so now I take the theorem. Oh, that should have been a theorem. HK. I take the theorem and I put D to be the classifying space of the natural numbers. Now I get decomposition space over the classifying space of the natural numbers like this. And over here I get pre-sheaf on this subdivision of the natural numbers, and that's delta inert. So the only missing thing is to see that this equivalence, this one actually is left Kahn extension, and that's where you need this one and some more work. But these are the main ingredients in this one. So there will be two papers with Philip, and the second, this one, I don't know if it's the first or the second, but it turns out that these, so we call these, the ones that arise like this, we call free. So they're the free decomposition spaces. And it turns out there are plenty of them in combinatorics. So we have a very long list of classical coalgebras in combinatorics that all come from free decomposition spaces. Okay, now I would like to just look a little bit outward from this theorem here. Let me see how much time. 5 minutes, is it okay?
Yes, yes.
So Louvier was involved in a lot of this coalgebra stuff in the 80s and maybe even earlier. And he found a universal Hopf algebra. Of something called Mobius Intervals. So an interval is just a category with an initial and a terminal object. Möbius is a finiteness condition. And what he showed is that for any coalgebra coming from, this is the coalgebra spanned by the arrows in a Möbius category. There will be a coalgebra homomorphism to this one. And Möbius inversion here, which I did not talk about, is induced from Möbius inversion here. So it's like a universal Möbius function. Unfortunately, this universal Hopf algebra does not come from a category. So it's universal, it's outside the class of objects it's universal for. But we proved with Galvez and Tonks that it comes from a decomposition space U, and it's a decomposition space of Mobius intervals, of course. In other words, this is just another instance of this principle. I claim that all combinatorial Hopf algebras come from decomposition spaces. So we could write down this one. And now that we have it, and it's on the same footing as all the other decomposition spaces, we could conjecture the following, that for any X decomposition space, the mapping space of Kulf maps from X to U is contractible, so that it is really universal. So Lovere found it but could not pinpoint the universal property because it was outside the scope of what he had as input. So it was quite natural to conjecture that now that we have everything inside decomp, this is true. We could not prove it, unfortunately, but we did prove it is connected. So Lovere essentially proved that it's non-empty, or maybe I should say inhabited, because he gave the interval construction, which is the one that this one comes from. So Lovere found an element here. We proved that it's connected, but we could not prove that it's contractible. So if it's contractible, then it's almost like saying that it's a terminal object in here. However, there's a size issue that in order to receive from all decomposition spaces, this one has to go one universe up. But if you restrict to Möbius decomposition spaces, so certain finiteness conditions, then this will actually live in the same universe. So in that case, the conjecture says that U is a terminal object. Now, we don't know if it's true. My student, Wilson Forero, has proved it for discrete decomposition spaces. And in that case, U is not discrete, it's a simplicial groupoid. So that's what you expect from higher topo theory, that when you find universal objects, you have to go up one categorical step, so that you will not find it a true universal object until you get all the way to infinity. So for discrete X, he proved that there is such a U, and it's a simplicial groupoid, so that this is contractible. So it looks good, and hopefully it will eventually be true. Okay, so if we now have a terminal object in decomp, then decomp is of course equivalent to decomp slice over that terminal object. So if the conjecture is true, if conjecture true, then decomp is of course the slice over this terminal object, and this is an infinity topos. So The theorem here is an important step towards proving that the category of decomposition spaces and Kulf maps, at least in the Mobius case, is actually itself an infinity topos, which would be quite surprising. But it could be useful. For example, then you can use homotopy type theory to reason here and so on. So that would be really nice. So Wilson is working on the general case, and of course it's much more difficult than the discrete case, but I hope he will succeed, in which case the category of decomposition spaces will have been proven to be a topos, an infinity topos. And I think that's a place to stop.
Thanks very much. Let's thank the speaker. And if there are any questions, please unmute yourself and ask.
I have an easy one. So I think I missed how decomposition spaces are in infinity category. So you gave us the objects and the one morphisms. Do you then just take a nerf, or do you localize with respect to something?
So inside the category of simplicial spaces,
Okay, got it.
you take the objects are the decomposition spaces, and for each mapping space you restrict to the Kulf maps.
Okay, and then you take whatever is left from simplicial spaces. Thank you.
Yes.
Any more questions?
If nobody has one, I will ask another one, which is probably also naive. So you said from the Lovier's result, you can recover this object I, but so maybe I missed once again, I maybe should know, if you take a Mobius decomposition space, it's coming from such a Mobius intervals co-algebra?
No, I mean, you start with any Mobius decomposition space.
Yes.
And then there is a Kulf map into U. And so U is about its one cells. So U1 are the intervals.
Okay.
U2 are the subdivided intervals. UN are the n-fold subdivided intervals.
Okay.
And what you do is you take one simplex, which you think of as an arrow. So here is your arrow. And then the corresponding interval will be the cloud of all possible two-step factorizations of this arrow. That would be the interval IF. So this is natural. I mean, suppose this is a category and this is just an arrow. Then this is a category where the objects are factorizations and the morphisms are diagrams like this. So that means it's a 3-simplex instead of a 2-simplex. So this is what the Lovier's interval construction does. And he wrote it down for categories, of course, but it's easy to generalize to decomposition spaces.
Okay, awesome. Thank you.
Maybe a quick one too. Did you look at what happens when you replace delta as a Kleisli category with the Kleisli category for a different familiar monad?
That's a very good question, and the answer is no. Well, we looked at it, but we did not really start to study it. But you could certainly do a lot. For example, instead of taking delta, you could take the dendroidal category omega of Mordyke and Weiss. It has the same active inert factorization system. And again, you can generate it by the free operand monad on the inert part. You get the whole omega. So there are many of the notions that make sense, and you could just write down something. but we have not done anything, and it's not completely clear what should come out of it.
Okay, funny. Thank you.
Anyone? Another last question, maybe? Or more? Well, if not, let's thanks for another time our speaker.
Thanks.
And thanks again to the first speaker and to anyone that came here. Thanks a lot for coming. We will be back, I think, in June. At the end of June, we will give you more information in the future. But for the moment, thanks for coming.
Yeah, thanks for coming.